Okay, so today we're going to be talking about Sn1 and Sn2 reactions and the difference between the two. So essentially, Sn1 and Sn2 are just substitution reactions where a leaving group is replaced with a good nucleophile. So let's just draw a little example. Or it would be like that. Ooh, that's the wrong button. So OH, the good nucleophile, replaces bromine, and now OH has taken its place. So that's just the most simplified, easy to understand substitution reaction, but they are a little more complex than that. So you might be thinking, what's there between Sn1 and Sn2? So Sn1 is a two-step process, while Sn2 is a one-step. And that may be a little confusing because Sn1 is two steps, and Sn2 is one step, but that's just kind of how it works. So let's just draw a Sn2 reaction just to get you a little example of one. So we have the leaving group here. Let's make it bromine. And in the case of an Sn1 reaction, because we're doing Sn1, I have the chart here, which you may be pretty familiar with or seen before. If we're doing Sn1 reaction, and this would be a tertiary substrate here, because you look at this carbon besides the leaving group, we have 1, 2, 3. So the substrate would be like that. It would be tertiary because there are 3 constituents that are not hydrogen here on this leaving group. So this bromine, this is a leaving group, but we have 1, 2, 3 other groups attached to this carbon. So that would make it a tertiary substrate type. So we're only talking about Sn1, Sn2. We're not going to be talking about E2 or E1 in this. So you can kind of just forget that for now. But we will have to be, if we're not doing E2 or E1, we're going to have to use a weak base and a strong nucleophile. So let's draw that out. NaCl. And we know it's a two-step process, so we might be thinking, well, what's the first step? It will not immediately, oh, my bad. It will not immediately replace the bromine. The Cl will not immediately replace this. So the first step, bromine, says, you know what? I do not want to be here. I'm electronegative. I am happy being on my own as a anion. Let me get out of here. So bromine leaves, and it exists essentially as this. It says, I'm out of here. I'm leaving. Get me out of this carbon structure. So what would it look like after it leaves? It would form a carbocation. So this would be the new structure of this original molecule here. It will now look like this. So this is step 1. It will exist like this. It is a carbocation. And if you know anything about carbocations, you would know that they like to rearrange if they could be more stable. But in this case, this is already tertiary carbocation. It is stable how it is. It has 3 groups, constituents attached to it. It is doing okay. We do not need to do any rearrangement. So next step, chlorine says, you know what? I'm okay being alone, but let's get rid of why have a positive charge if I have a negative charge? Let me donate that. Let me donate some of my electrons to make a covalent bond, and let's get rid of our charges. So it will attack the carbocation. That is a nucleophilic attack, and we would have the end product looking like this. Let's get that out of the way. So this is the end product. After step 2, it would look, I'm just going to, step 1, we can have that on the side, but the end product would be this. The end product of Sn1 let's just draw Sn1. It would look like this. And if you were given a question, which I should talk about this, if you're given a question that has indicated stereochemistry of the bromine, let's say bromine's on a wedge here, I'm not going to fill it up all the way, and say this is on a dash, that carbon's on the dash. So how can we what would be the indicated stereochemistry after, given its Sn1, if chlorine attacks and it's Sn1, what would this be? Would this be a wedge? Would this be a dash? So, interestingly, this would actually be both. And you might be confused saying, well, how is it going to be both? There's something called a racemic mixture. So let's just kind of write that down because that's a pretty big thing to know. It is a 50-50 split of stereochemistry. So this Sn1 will be racemic. So let us just draw out what that looks like, because you might be thinking, well, how is it going to be a split if it's going to be 50-50? So if we had, say you're in the laboratory, say you had your OChem lab, and I didn't mean to do that. Say you have your OChem lab. Jesus, okay. Say you have your OChem lab. Okay, I don't know why it's looking like that. You're just going to bear with me here. Say you have your OChem lab, and you have this molecule. This is your starting molecule, and you react it with NaCO. If you looked at the end product after that reaction, or this, say you had this given, let's just move that there, make it easy. This starting molecule would look like both of these. There would be a 50-50 split. Say you had 1 gram. Sorry, that looks like this molecule looks pretty bad, but you just have to bear with me. If you had, say you had 1 gram of this starting molecule, you would have half a gram of this and half a gram of that, where the chlorine is on the dash, and then you have one where the chlorine is on the wedge. So it's racemic, 50-50 split, because if you think about it, it does make sense, because let's draw that carbocation once again. So if you had this is the carbocation, it's chilling here. This is trigonoplanar. So technically there is no, this is flat right now. This is flat. There's no there's no 2 or 3D aspect to it. It's flat. All 3 of these have a 120-degree angle. I guess I can just draw that just in case you were wondering. 120-degree angle. So when chlorine comes in here, there's no real defined way for it to attack, because there's nothing's sticking one way. There's no stereochemistry here. They're all linear, or they're all flat. So it basically has to attack one way or the other, but it's not really defined. There's no easier way for it to attack, so it just attacks both at the same time, giving us the racemic mixture. So that is Sn1. So let's talk about Sn2, which I think is much simpler, honestly. So let's say we have pentane and we have chlorine, a good leaving group. Let's just check that off in our head mentally, and we're reacting it with a good nucleophile. Let's do OH. Let's just do NaOH. So we're reacting like this, and let's think, okay, well, the leaving group, is it tertiary, is it secondary, or is it primary? Well, if you look at this, we have 2 hydrogens here and only one other big constituent, like considerable constituent, I suppose, that's how you could say that. One big group. So there's only one, and then we only have one. So we can say this is primary, because if this did leave, the carbocation would be a primary carbocation, which we know we do not want. So let's just bring it back level. So we know, let's think about Sn2. This is Sn2. This is 1 step. The reason why it's only on 1 step is because OH is dying at the opportunity to take its place. It says, I don't want to be negative. If you're leaving, if chlorine, as we said, it's a leaving group, it wants to leave, OH says, let me get in there. I'm going to replace that the second it's gone, giving us the end product that would look like this. And now if we had stereochemistry, let's say we have this molecule and let's have a wedge, chlorine. There's also a hydrogen there on the dash, and it's reacting with the same thing. Let's have NaOH. Now the end product would, let's draw this out. You might be thinking, well, is it going to be racemic like earlier? No, it would actually be, the stereochemistry would now be inverted between the reactant and the product. So chlorine, the leaving group, was on a wedge. Now it's on a dash. Because OH, the way it replaces this chlorine is that it's called a backside attack, where it would attack through here. So this is leaving, and then OH attacks on the other side, saying, I need to be there. I don't want my negative charge. And it stays. It basically bumps up this hydrogen, if you think about it. Hydrogen's now on a wedge, and OH is now on the dash. So that is all well and good. Let's draw this. Sn. Oh, I don't know why that's so small. Sn2. Oh, I should probably draw that a little better. Sn2. So you might be thinking, well, okay, just so you understand, I drew this reaction here on the chart. Looking at this chart, that would be this here. We had a tertiary substrate, and we had a strong nucleophile. So this would be what we drew up here, this Sn1, this would be this version of Sn1. And this Sn2 right here that we have, this starting group, or this starting molecule, would be an example of this. We have Sn2, substrate type, it's a primary, and we have OH isn't on here, but you can just assume like OH, just have that right there. OH is a strong nucleophile. Oh, actually, sorry, it would be this one. Yes, it would actually be this. So, excuse me, it would be this. I was wrong. It would be primary, OH here. It would be this version Sn2, and then this one below, it's secondary, and we also have Sn2. So, I'm not going to E2, but you might be thinking, well, you explain this, explain this, explain that, and you can think Sn2 pretty much acts the same if it was one of these groups, because we know it's Sn2 there. So everything, well, what about this Sn1? You didn't talk about that. So let's talk about this. Let's go back to Sn1. We have bromine, and this, it would have to be tertiary. Yep, bromine here. So that means this is a tertiary reacting with, let's do H2O. So you might be thinking, well, hold on, water is not a very good nucleophile. It has no charge. It doesn't have a negative charge. Why would it act like a nucleophile? So essentially, how this would work is that we have the same thing happen. Carbocation, bromine leaves, and then H2O will eventually attack here. Let's draw it with the proper line. OH would be here. And well, hold on, why does oxygen have 3 bonds? It doesn't want to have 3 covalent bonds with only 1 lone pair. It wants to have 2 lone pairs and 2 covalent bonds. So eventually this hydrogen, for the sake of just making it simple, let's have the bromine, which would still, if we had this in lab, bromine would still be sitting somewhere dormant in this mixture of this starting molecule and H2O. So bromine, let's just assume bromine says, you know what, let's get rid of this hydrogen, and takes that. So this would go to the, oh, that was a really bad line. Hydrogen, the covalent bond would go to the oxygen, and bromine would take the hydrogen, giving us the end product of this. OH. So a common mistake that I've seen from a few people is that if you might think, well, hold on, bromine, H2O. So let's think about it. Why don't I just put it's if it's Sn2, Sn1 or oh my god, sorry. If this is Sn1, let's just make it's OH here. It's H2O. That's the nucleophile. So H2O would be here. But no, it would actually still be OH because it gets deprotonated and loses its hydrogen. So I hope that gave you a little bit of insight onto Sn1 and Sn2. They are very confusing to understand. If you were confused about nucleophiles and electrophiles, you can check another video that I have on my channel explaining simply what nucleophiles and electrophiles are. I am still an undergrad student, so please let me know if I got something wrong. I'm sure I did. And thank you for watching.